Hi, everybody. Thank you so much for being here today. My name is Aashreya Govindu, and today I'm presenting my work this summer on measuring stellar motions in the context of the stellivore hypothesis. So just a quick agenda of what I'm going to be going through today, the idea, why I use spider pulsars, the question, the analysis pipeline, the results so far, and what we plan to do next. So the idea that started this project came from my advisor, Dr. Clement Vidal, with the stellivore hypothesis. So basic idea relevant to my project specifically is that a hypothetical star-consuming system could potentially move from one stellar environment towards a different one. And what matters for my work is this gives us a very testable question, its motion. So if we want to see whether an astronomical system could move towards a different one in a certain amount of time, or maybe it already passed one in the past, we need to be able to study its trajectory. And in order to do that, we need to know how its position has changed with time or will change with time. And we need proper motion, which is the apparent angular movement of an astronomical object across the sky. And it's usually measured in milli-arcseconds per year. So for any of you who know what an arcsecond is, that's about 1,000th of that. So it's a very, very small, very precise measurement. And through the previous work done towards this hypothesis, one question that was raised is, are these proper motions accurate? Because if we're doing trajectory analysis, but our data is wrong, then the analysis is sort of also wrong by result. So before I get into that, I want to go through what spider pulsars are, because when I started this project, I also had no idea what a spider pulsar was. I knew what a pulsar was, so which is a rapidly rotating neutron star, but spider pulsars were new to me. So before I needed to know what that is, I needed to know what a millisecond pulsar was, because that's what Google told me a spider pulsar was. A millisecond pulsar is a pulsar rotating extraordinarily quickly. It's oftentimes hundreds of times per second. So it's very, very, very fast. And spider pulsars are millisecond pulsars, but they're also in very compact binary systems with very relatively low mass companion stars. And they're called spiders because they irradiate material from the companion star over time. So essentially, it's two objects in a gravitational binary system. So in order to get the data about both of these objects, I used the ATNF, which is the Australia Telescope National Facility, to get data on the pulsar, and then Gaia to get data on the companion star. Gaia is an ESA astrometry mission, and it actually makes measurements on various astronomical objects, not just these stars. And so then when I had both of these measurements, since they're in a binary system and we check motion, in theory, they should be exactly the same and they should correlate. And they did a lot of the time, which is encouraging. But there obviously are always outliers. So that's something we need to investigate further. And I will come back to that in a little bit. So the immediate question that I was trying to answer this summer is the proper motion of the Gaia companion as good as, better than, or worse than the proper motion data from the pulsar? To do this, I sort of broke it up into three main parts, the first being getting data from Gaia. So I used the most recent release of Gaia, which is Gaia DR3, and then I took the right ascension motion and the declination motion, which you can kind of think of as perpendicular movement in the sky. And I added that to the SpiderCat dataset, which was existing. Then I compared Gaia with ATNF, so I also got the RA, right ascension, and declination data from there, and I was able to do that comparison. And I also wanted to compare across the different releases from Gaia itself because it had DR1, DR2, and DR3. And so I wanted to see to make sure there was correlation there as well. So speaking of analysis, building my analysis pipeline was a lot more data analysis than I thought it was going to be coming into this project, which made it just as rewarding when I actually got the code to work. So the first I started with SpiderCat, which has 126 spider pulsar systems. And then I was going to just simply compare it to Gaia and then move on from there, which sounds great in theory, but unfortunately, the Gaia IDs in the working CSV file that I had were rounded into scientific notation, which then messed with the actual number itself. So when I was trying to compare them, it kept coming up with no matches found, no matches found, which I knew shouldn't have been the case. So instead, I decided to reconstruct the expected sky position and then try to find the DR3 match that way. And then when I felt like I had a reliable source, I would get the proper motion, its uncertainties, and the renormalized unit weight error as well. And then I could compare that back to ATNF and do that comparison that way. So in this source recovery from the 126 SpiderCat systems, 63 of them I was able to find a high quality match. Everything was great. 17 of them, there were a few inconsistencies here and there that I had to check for, so I had to review those. 44 of them, unfortunately, had no Gaia source within 5 arc seconds, so couldn't really use those. And then 2 of them, I couldn't reconstruct usable coordinates at all. So again, unfortunately could not use them either. And it was really important to me throughout this process to be very rigorous with this testing because if anything is mismatched, it could cause an artificial result. And it wouldn't necessarily mean that either catalog was wrong. I would just be looking at the wrong star, which would mess with my analysis and nothing else. So the strongest result that I have so far is the Gaia DR3 versus the ATNF, which I have that plot here on the left. So the dashed line that we can see in the middle here is the one-to-one line. So anything on or near that line is a almost perfect numerical match. And as we can see, it's very encouraging that most of the points are on or very close to that line. Obviously, there are some outliers and disagreements, which aren't necessarily failures in the analysis. They're more just, okay, we need to go see what the problem is here and if there has to be more analysis that needs to be done. And one of the specific questions that I do want to look at as I continue this is the ATNF measurement actually independent from Gaia, since ATNF has various sources that go into it. So that is one thing I do need to work on checking. So another way of comparing the measurements is precision. So here I have the formal uncertainties associated with the proper motion measurements. So I have 0.3 and 0.26 for the Gaia DR3, and then 0.4 and 0.6 for the ATNF. And the Gaia DR3 uncertainties are significantly better than the DR2, which were 0.63 and 0.54 respectively. And the ATNF's higher uncertainty can again be attributed to the fact that it has various sources for its data. So if the sample size is different or if the sample size was measured differently, then it could also account for those higher uncertainties as well. So coming back to the outliers, I formally looked at 2 of them. The first being J1959, which was a mismatch on the Gaia part, was what I could come to understand. So I have to go in and verify the optical counterpart and check the Gaia quality to make sure that maybe I looked at the wrong Gaia star or if there was like a problem with the data. So that is an ongoing analysis, but I have been able to ascertain that it was a problem on the Gaia part. And then for J2215, the mismatch actually came from the pulsar side. So I need to trace the ATNF reference before I can conclude, okay, maybe it might actually be Gaia's fault and not ATNF. But for the most part, it seems like it's an ATNF problem. Then, like I mentioned before, I also did a release to release check on Gaia. So I did DR1 versus DR2, DR2 versus DR3, and then DR3 versus DR1. Unfortunately, DR1 had no usable proper motion overlap, so I don't have a graph for that because it would just say there is no overlap, and that's not very fun to look at. But DR2 versus DR3, I was able to find 47 apparent overlaps. But as we can see here, there's a lot of scatter, which I was not expecting because there shouldn't be that much difference between a release to release since it's technically still looking at the same part of the sky. So that I can't chalk it up to physical motion yet because I haven't done that analysis and I don't want to make that assumption. But it is under validation and I need to go back in and test for the ATNF provenance and see, okay, why is this scatter happening? And I hope to have answers as to that soon. So with that part done, now I'm working again on checking the outliers and the ATNF provenance to see where all the data is coming from and sort of do that trace back. And then I'm also going to validate the DR2, DR3 to see where that scatter is coming from. Beyond that, we want to do final uncertainty statistics because the uncertainty is obviously very important and it can prove that, okay, our data is really good, or okay, maybe our data isn't as good as we thought it was. And then following that, we obviously want to do the close encounter trajectory analysis from the very beginning and see what we can understand from there. So these are just some key takeaways that I hope I've done a good job of highlighting throughout my project. And with that, thank you so much, everyone, for being here today and listening, and I can take any questions.